It is now time to start up COMSOL Multiphysics version 4.4. When COMSOL starts, choose Model Wizard. At the Select Space Dimension stage, select 3D since you are going to model the bearing color as an elastic solid. Then double-click the Structural Mechanics physics to unfold the different physics to choose from. Select Solid Mechanics and click Add. On the right, you will now have a Review Physics panel stating the dependent variable, which is the displacement field u. The x, y, z components of the displacement field are also given here. You are free to rename them too. But let's have them like this, and let's try to remember that w is the z component, since this is the component that would show up in the film thickness equation in the Reynolds equation. Now click the Study arrow. You will now be given the option to choose which type of study you are about to perform. Choose Stationary and click the Done tick box below. You will now find yourself inside the COMSOL GUI for modeling and simulation.
There are 7 tabs plus the File menu, and below there are 3 panes: Model Builder, Geometry and Graphics, going from left to right.
It is the Model Builder pane which determines the content of the middle pane. Geometry is open since Geometry 1 is selected in the Model 3 in the Model Builder pane. Before we proceed, let's save the model for future use and to have something to restart from when things go wrong. Click the diskette icon or unfold save from the file menu, or use the shortcut Ctrl+S. I will save mine under the name cylindricalstepbearing.mph. MPH, by the way, stands for multiphysics, in case you were wondering about that. Since we are going to model a segment of the color, which is a cylindrical shape, we will first define an XZ work plane. Then we will revolve this plane around the Z-axis to generate the color segment. Let's proceed by right-click Geometry 1 and select Work Plane. The middle pane now changes to Work Plane, and you are now going to use the plane drop-down menu to select an XZ plane. Leave the other properties as default for now and right-click Plane Geometry and select Rectangle, as this will be the cross-section shape for the color segment. It is now time to generate a bunch of global definitions that will be used to describe the problem at hand. To do so, right-click Global Definitions highest up in the Model 3 and choose Parameter. In the Parameters pane, you can define the input for the problem. We will, instead of typing them in one by one here, now instead load a set of predefined input parameters from a file. Click the Open Folder icon below the parameter list window and browse to the folder where you have saved the input parameters.txt file that you've been provided with. Mine is in the same folder as where I saved the model. Select the file and click the Open button down to the right. The Parameters pane is now filled up with a set of inputs specified in the file. These include dimensions as well as descriptions. Take your time and review them so you have a good grip on what can be found there. Select the rectangle again and type in RO minus RI plus 2 times RF in the width box. Type pad underscore T in the height box. Then type Ri minus Rf in the XW field in the position for the corner. Type minus pad underscore T in the YW field in the position for the corner. The width of the part of the collar which will interact with the hydrodynamic pressure is now RO minus RI, and the top surface of this collar segment is positioned at Z equals 0. RF is just the fillet radius and is introduced here to add some more reality to the problem. Now click Build Selected in the top of the rectangle pane. You have now built the cross-section for the collar segment, including some extra width for a fillet radius on the inner and outer verges of the collar. This cross-section is depicted as a shaded rectangle in the graphics pane to the right. Let's add the fillet radius to the corners of the collar cross-section rectangle. Right-click Plane Geometry and choose Fillet. In the graphics pane, click the corners of the rectangle. They will become blue and slightly larger when properly selected. Moreover, in the fillet pane, which is now open in the middle, you can see a corner tree. That indicates that you have selected the corners you intended to. In the radius box, in the fillet pane, type RF to define the fillet radius as RF. Then click Build Selected in the top of the fillet pane. The graphics pane will now be updated with a new cross-section including the fillets, and we are now ready to revolve it around the Z-axis to generate the collar segment. To do so, right-click Workplane 1 and select Revolve. In the middle pane for Revolve, you can now type in Revolution Angles. Leave the start angle as 0 and type in θs in the end angle field. We will actually create two similar cylindrical segments, that is, this one that starts at 0 and ends at θs, and another one that starts at θs and ends at θp. The reason for this is to provide for a good mesh that considers the step in the bearing geometry in an adequate manner. Finish the revolving by clicking Build Selected. The other segment can be easily defined by right-clicking the workplane 1 and then selecting Duplicate. Now work on workplane 2 till you obtain the full collar segment. It will be looking something like this when you have clicked Build Selected. Note that you will need to create another revolve for the duplicated workplane.
The only bit that is missing now is to properly unite these two collar segments. This is achieved by forming a union. You can either utilize the Geometry tab or by right-clicking Geometry 1, choosing Boolean operations, then selecting Union.
With the Union pane open in the middle, hold Shift and left-click each of the segments in the graphics window. They change color from pink to purple when they are selected. Finish by Build Selected. Notice that you are meant to keep the interior boundaries in order to provide for better meshing possibilities. You are now finished with the geometry of the bearing collar. Next up is setting up the material and the solid mechanics model, including defining boundary conditions. After that, you will mesh and finally simulate the multi-physics problems of thin film fluid structure interaction caused by the hydrodynamic pressure buildup inside the fluid film.